This video covers modules 26 through 28 notes, and it is the first look into Unit 5, Land and Water Use. So we'll go through kind of a hodgepodge of topics over the next few videos. First, we're going to look at the availability of water. About 70% of Earth's surface is covered by water, and almost all of that, over 97%, is in the ocean, making it salt water. The remaining less than 3% is fresh water. Of the fresh water on Earth, about 77% is found in ice and glaciers. A quarter of it is below groundwater, and the rest is found in bodies of water and in the atmosphere. We're going to take a deep look at groundwater, which is about a quarter of all of the fresh water on Earth. Groundwater exists in small spaces found within permeable layers of rock and sediment called an aquifer. There are two types of aquifers. They can either be unconfined or confined. In unconfined aquifers, they're going to be made of porous rock and covered by soil, so water can easily flow in and out. With a confined aquifer, the water flow is going to be impeded by a layer of impermeable rock or clay. Then when we'll talk about the water table some, that's just the uppermost level at which water fully saturates rock or soil. So in figure 26.2, you can see an example of where the water table is and an example of an unconfined and confined aquifer. Groundwater does have to be, or we'll talk a little bit about groundwater recharge, which is how water percolates through the soils and works its way into an aquifer. But note there that confined aquifers can only be recharged if there is an opening in the impermeable layer of rock. So that's seriously going to decrease the rate at which it can recharge. One of the benefits of aquifers is that plant roots can access water from them as long as they're deep enough in the ground or the water table is high enough. And springs can form when water from an aquifer percolates up to the ground surface. And those are good sources of water for humans and organisms that live in aquatic biomes. Humans also drill wells, which is a hole that will go down into a confined aquifer. So let's go back and look at figure 26.2. On the far side, we can see that that well is dug down deep enough to be able to access water from the aquifer. How long water has been sitting in an aquifer is going to vary. It's going to be recharged a little more frequently and will have more water movement in an unconfined aquifer because water is not going to stay there as long. The issue, though, is that it is more likely to be contaminated by chemicals. In a confined aquifer, water can stay there for thousands of years, just depending on how long it's there, whether or not humans are taking water from it, etc. The largest aquifer in the United States is the Ogallala Aquifer. It's found out west from here, where we live. And the problem is that large amounts of water have been withdrawn for household, agricultural, and industrial usage. And it does have a very slow rate of recharge. So if we keep taking out water faster than it's replaced, there is a high likelihood that it's going to run out of water sooner over later. In figure 26.4, you can see two things. First is the water level change in meters. Some of it is relatively neutral. Maybe we're at plus or minus 3 meters, but there are several spots where there is between 7 and 45 meters of change. And the other thing you can see is the saturated thickness of the aquifer in meters. What happens when we remove more water than it can be replaced with? First, the water table is going to drop from the ground surface, and then the springs will stop emerging, And so all of those spring-fed streams are going to dry up. Another problem will be that the shallow wells will not be able to reach the water table. So those wells will not be able to give water to humans. And when that happens, it creates an area that contains no groundwater around the well, and that's called the cone of depression, which we can see here. So in figure 26.5a, you can see what the area looked like before heavy pumping. We've got 3 wells in this area, and you can see where the water table line is. After heavy pumping in 26.5b, you can see that the water table has lowered. 2 of the wells no longer have access to water, and we have that cone of depression around the well in the center. Saltwater intrusion can also happen closer to the coastline, where an infiltration of saltwater in an area, or there is an infiltration of saltwater in an area where groundwater pressure has been reduced from the extensive drilling of wells. And that's going to be a problem because we do not want to have any saltwater intrusion on our fresh drinking water. Surface water is the collection of our aquatic biomes. Recall that surface water is the above ground fresh water that includes streams, rivers, ponds, lakes, and wetlands. Early civilizations settled along larger rivers because the land around the river is usually going to be pretty highly fertile, and so agriculturally that's going to be better. The floodplain is all of the land that's adjacent to the river. And rivers will naturally overflow and go across that flood plain, leaving behind really nutrient-rich sediment, which makes it, you definitely want to live there so you can plant food there. Sure, it might flood every now and again, but having a nutrient-rich soil is good for plants. There is also some water in the atmosphere, and that will eventually be precipitation. And this is a very small percentage of our Earth's water, but it is essential for people who live in arid regions. Some issues that we need to talk about real quick are drought and flooding. Drought can lead to a decrease in crop yield, which does lead to starvation of humans and other organisms, and it does have a negative impact on soil. The soil is going to dry out and not be as nutrient rich and not be able to support as many living things. Flooding is a bigger problem for areas that rarely flood because they don't have a system to capture that excess water. And flooding is made worse by some human activities like creating impermeable surfaces, like parking lots, buildings, and things like that, that don't allow for water penetration. So normally over land, when it rains, eventually that water will be absorbed by the soil. But if we have an impermeable surface there, that's not going to happen. Got to wait for that to evaporate. Next, we're going to look at the human alteration of water availability. And we do that by several different things. First, to help prevent flooding, humans have built both levees and dikes. A levee is a enlarged bank that's built up around each side of a river. Some issues with that are the surrounding land will have reduced fertility. The sediments will travel further downstream and end up where the river enters the ocean. So instead of that sediment being spread out, it's all clumped up in one space. And it also forces flood water farther downstream, which is a problem for places there that are farther downstream. They will have an increase in flooding, and it encourages development in floodplains, which is going to be a big problem if for whatever reason that levee breaks. A dike is a similar idea, but it's built to prevent ocean waters from flooding the adjacent land. And there's going to be issues with that, similar issues as well. Humans also build dams to restrict the flow of streams and rivers. A dam is just the barrier across a river or stream to control the flow of water, and the reservoir is the body of water created by that dam. We've already talked some about this when we did our energy unit, so I'm going to leave this to be kind of brief. But one thing that is a problem with dams is that it restricts where fish can go. And so we have included fish ladders, which are stair-like structure that allows migrating fish to get around a dam. Because they do still need to be able to migrate, or that's going to be a problem for that fish, and also probably eventually for humans as well. Aqueducts carry water from one location to another. So an aqueduct is a canal or ditch that's used to carry water. We can, using them, remove water from a lake or a river to a place where it is needed. Both Los Angeles and New York City rely on aqueducts to meet their daily water needs. So without that, they would not be able to supply enough water for what the demand is there. But there are consequences with that, which we can see in figure 27.5. The sea has been, let's see, they added a dam, and you can see that over time that water has dried up. Desalination or desalinization converts salt water into fresh water. And the two most common techniques for that are distillation and reverse osmosis. For distillation, that water is going to be boiled and steam will be captured and condensed to yield pure water. And with reverse osmosis, water is forced through a thin, semi-permeable membrane at high pressure. And here in figure 27.6, you can see picture examples of both of those techniques to take unusable water and make it usable or drinkable. And in this figure 27.7, you can see the freshwater availability around the globe. Last, we will talk about human use of water now and in the future. Most of our water use is for agriculture. So when we talk about our water footprint, that's our total daily per capita use of fresh water. And that's going to vary among countries, which you can see in figure 28.1. It's going to be a little bit higher in developed countries and a little lower in developing countries. Water is going to be necessary for irrigation and hydroponic agriculture. There are 4 major irrigation techniques. The first one is furrow irrigation, where a trench is dug and flooded with water. A flood irrigation is where the entire field is flooded with water. Spray irrigation, which is probably what you're most familiar with and have seen while you're out and about, is there is some sort of apparatus that sprays water across a field. And drip irrigation is where there is a slow dripping hose that is laid on, or maybe it's buried beneath the soil. And that's actually going to be the most efficient, but it's probably not the most common. In order to conserve water, making major changes to our irrigation practices is going to be essential, because that's where most of our water use is going. Hydroponic agriculture is an alternative to traditional irrigation, and that is the cultivation of plants in a greenhouse like space, and it immerses roots in a nutrient-rich solution. And so these plants are kind of going to be like floating on a water, and it has a pumping system that will move water and nutrients around to make sure that all of whatever is growing there has access to that. Some advantages are that it requires little to no pesticides because it's going to be grown indoors. It uses 95% less water than traditional irrigation, and crops can be grown year-round and not only during their growing season. So I think going forward, I'm noticing that hydroponic agriculture is becoming more popular, but we'll see. Water is also used for industrial processes and in households. In examples for industrial water use would be for generating electricity, cooling machinery, refining metals, and making paper. Household uses would be drinking water, washing machines, bathrooms, watering lawns, washing cars, pools, and a bunch of other things I probably have not thought of. Here you can see in figure 28.5 per capita household water use by country. And surprising, the US is not number one on this one. So that's encouraging. And then in figure 28.6, you can see the percentage of indoor water use, and that would be for the US. So first is flushing the toilet, followed by bathing, laundry, and then cooking and drinking water is last. The future availability of water depends on both water ownership and water conservation. So the big question when it comes to water is who owns it? Does anybody own it? And that very issue has created conflicts throughout the world of people thinking like, okay, this is my water, I can bottle it and sell it, or, this body of water belongs to this country and things like that. And then finally, another big one is water conservation. So, how can we use technology to reduce our water use? And some of that we already have coming. So, a lot of places will now have the low flow toilets. As we saw, that is our biggest water use in households. So, using less water to flush toilets and things like that. We can also, collect rainwater to water plants instead of using garden hoses and things like that. So lots of options for conservation, but that will be necessary to continue for us to continue to be able to use lots and lots of water going forward.